Intro to waves. So what are waves? Waves are a method of transferring energy from one point to another. Waves transfer energy without transferring matter. For example, when light waves are transferred from your computer screen to your eyes, only energy is being transferred. To travel from one place to another, a wave vibrates or oscillates. Looking at the displacement and distance graph, displacement is how far the wave oscillates from the equilibrium point, while distance is how far the wave travels from the starting point. Next is the wave characteristics. This point right here is called the crest, which is the highest point on waves, while this point right here is called the trough, which is the lowest point on waves. Next is the amplitude. The amplitude represented by A is the maximum height of a crest or a depth of a trough relative to the normal or the equilibrium level. From the crest to the trough is equal to 2 amplitude. This part is called the wavelength, which is the distance between two successive levels. The wavelength also equals to the distance between any two successive identical points. Wavelength is represented by a Greek letter called lambda. Next is the time period. The period represented by a big T is the time elapsed between two successive crests passing by the same point in space. In simpler words, the time needed to complete one oscillation. The formula for period is equals to 1 divided by the frequency. The frequency represented by a small f is the number of crests or complete cycles that passes a given point per unit time. In simpler words, the number of cycles completed in 1 second. The unit for frequency is called hertz. The formula of the frequency is equals to 1 divided by the period, or 1 hertz equals to 1 cycle per second. For example, from this graph there are a total of 2 oscillations in 1 second, meaning that the frequency is equals to 2 hertz. And the period is equals to 1 over 2, meaning it takes half a second to complete one oscillation. As we can see, the frequency and the period are inversely proportional. Transverse waves and longitudinal waves. First off, transverse waves. Transverse waves are the waves where the particles of the chord vibrate back and forth in the direction that is perpendicular to the motion of the waves itself. It has crest and trough. This is the particle motion and the wave motions of transverse waves. The particle on the crest will fall down and go up and fall down and so on. So the particles move up and down while the waves move to the right, bringing the particles as it moves it up and down forward as well. Some examples of transverse waves include light waves, water waves, and vibrating strings. Next is longitudinal waves. Longitudinal waves are the waves which the vibration of the particles of the medium is parallel to the direction of the wave's motion. This is the particle's motion in longitudinal waves, where this is the wave motion. Longitudinal waves are formed on stretched spring or slinky by alternately compressing and expanding one end. This part right here is called the expansions, sometimes referred as the refractions, which is the region where the coils are momentarily far apart. Where this part right here is called the compression, which is the area where the coils are momentarily close together. In longitudinal waves, compression and expansions correspond to the crest and the trough of the transverse waves. Some examples of longitudinal waves include sound waves and seismic P waves. Transverse waves versus longitudinal waves. These are the wave motions of both types of waves. In the case of transverse waves, a section of the medium in which longitudinal waves passes oscillates over a very small distance, whereas the wave itself can travel large distance. Next is finding the wave speed. Wave speed, represented by a small v, is the speed at which wave crest or any other fixed point on the wave shapes move forward. The wave speed must be distinguished from the speed of the particles of the medium itself. A wave crest travels a distance of one wavelength in a time equals to one period, meaning that the wave speed equals to the wavelength divided by the time period. Therefore, the wave speed equals to the wavelength times the frequency. Next is finding the speed of transverse waves. The speed of transverse waves depends on the properties of the medium in which it travels. The formula is speed of transverse waves equals to square root of ft over mu, where ft equals to the tension on cord and the mu is mass of cord divided by the length of cord. This formula only applies to cord or strings that has small amplitudes. This formula makes sense qualitatively on the basis of Newton mechanics, which states that when tension is greater, speed should be greater since each segment of cord is in tighter contact with neighbor, and the greater the mu, the more inertia the cord has, the slower the wave should propagate. Lastly is finding the speed of longitudinal waves. Speed has a form similar to that of transverse waves on a cord, where the formula for speed is equals to the square root of elastic force factor divided by inertia factor. For longitudinal waves traveling down a long solid rod or spring, the formula is equals to the square root of elastic modulus divided by the density. As for the longitudinal waves traveling in liquid or gas, the formula is equals to the square root of bulk modulus divided by the density. The elastic modulus and the bulk modulus can be referred from this chart. We come to the end of the video. Feel free to hit that like button and thank you for watching.